let's start. Couple of updates. We will not have a class on Wednesday, so you get a little bit of time off this coming Wednesday. I believe that your last assignment is due on Wednesday. Is that right? So you'll have time to, work on your assignment. Projects. You should have received project, updates from TA yesterday, and I think we've extended projects proposals by Friday. So let's make sure that people look at the feedback and such. Also talk to your TAs. And then after that, we'll have Thanksgiving weekend, and then a couple of more weeks, and then you have your projects are going to be due. Okay, so you're almost there. Think of it this way: if you finish your last homework, and you finish your 4-page project proposals, you only have to write 4 additional pages for your final project, right? So that's where we are. Any questions? Again, one thing I should point out is that look at GradeScope, look at the feedback. We're not going to be grading 1-page project proposals, like you're not going to get a grade, but look at the feedback. It's mostly for you to look at the feedback, because some projects were very good, some projects were not so good. Okay, so make sure that you look at the feedback of TAs, and also if you have any questions, talk to your TAs, and also talk to me during office hours, okay? Yes? Yeah, if you're switching your projects for some reason, because you figured out, your previous project, something is wrong or something doesn't work out, you want to switch the projects, your 4-page project proposal, you're welcome to do that. Right? But again, just make sure that sometimes the feedback from TAs, things like be coherent, write coherently, clearly state what the problem you're trying to solve, what data sets you're going to be using, what models you're going to be using, what conclusions you're going to be drawing, right? If you don't have that in your final project, then you're not going to get a good mark. Does that make sense? Think of it as writing a paper, right? It's your way of writing a paper and submitting it to the conference. So make sure that it's polished, don't have any spelling mistakes, and, formatting is all wrong and things like that, right? So this is a graduate level course, so you should be able to do that. Also, please make sure that you don't submit your project proposals in Microsoft Word. Or your final projects in Microsoft Word, right? And like using Microsoft Word equations and stuff like that, right? I think that you guys, most of you are graduate students, and the expectation is that you should be able to put together a decent project. Doesn't have to, receive a best paper award at a top tier conference. That's not what the expectation is. But at the same time, put some time into the project, okay? Any questions? And again, the encouragement is talk to TAs. Look at the feedback and talk to TAs. Okay, so today we're going to start looking at a class of methods called Markov chain Monte Carlo methods. Last time we've covered variational learning. Today we're going to look at MCMC methods. Those are the 2 dominant techniques for doing inference and learning in graphical models, but also in pretty much all of deep learning models. So today we're not going to cover the whole class. So we're not going to cover MCMC. We're going to continue next Monday. And then next week, we're also going to look at variational autoencoders, right? Which is kind of combines variational learning. And then we're going to look at MCMC extensions of variational autoencoders. And then the last couple of weeks, we're going to cover things like GANs, and also a little bit of reinforcement learning, just to show you what the spectrum of things are. Okay, and again, no class next Wednesday, and we're going to announce it on Piazza. Okay, approximate inference. So remember, this is just a reminder from the last class. We're going to be interested in evaluating the posterior over the latent variables, given observed variables. right? And in cases like expectation maximization algorithm or EM algorithm, we're going to be evaluating expectations with respect to something called expected complete data log likelihood, very much similar to what we've seen in the last class, right? It's the first term. And then for more complex models, when we can't evaluate the posteriors, we're either going to be using variational approximation methods, right? Something that we've seen in the last class. And today we're going to consider sampling-based methods. And these techniques are known as Monte Carlo-based techniques. Some of them are called Monte Carlo, some of them are called Markov chain Monte Carlo, and we'll see what they are. So in practice, if you pretty much look at any paper, anytime you have latent variables, so anytime you have a stochastic model, those are the two dominant techniques. Either people are using MCMC methods or variational methods, or combination of both. So these are two very, very broad approaches. Let me give you a couple of examples. There is a class of models called Bayesian neural networks. They basically were pioneered by Redford Neal back in the early 90s. And the idea is the following. We can think of neural network as a regression problem, right? So we're given a set of ID data, X, with corresponding targets, T. We can write down the likelihood function, right? And the likelihood function could be a Gaussian function if we're solving a regression problem. So we can write as a product bunch of Gaussians, where Y here is the mean is given by the output of a neural network, right? So it's a multi-layer neural network. It makes a prediction, and you put some Gaussian noise around. That's a standard way of solving a regression problem, right? If you take this output and put it through the softmax, you have a classification problem, right? So depending what loss function you're using. So we can write down the likelihood function, and if that's all you wanted to do, then you can just do some likelihood estimation. You could optimize this log likelihood function with respect to parameters, and that's exactly what we've seen in the last in this course, right? And this is just a sigmoid function. It could be ReLU, it could be 10H, whatever nonlinearity you want to use. Now, what we're going to do in Bayesian models, we're going to place a Gaussian prior over model parameters. Right? So we're going to say the prior distribution over the parameter is going to be given by a Gaussian distribution with some variance. And then what we're going to do is we're going to say, well, there is a likelihood function, which is a Gaussian. There's a prior, which is also Gaussian. And again, people study different kinds of priors. The posterior is going to be not analytically tractable, right? You can't really compute what's the optimal distribution of parameters because of nonlinearities. And in general, you can't really compute this term. You can't really compute the normalizing term, right? So what people do, people generally say, well, I can't really do that, but what I can do is I can look at the maximum a posteriori, do map estimate, which is essentially comes down to your standard optimization plus L2 regularizer in this case. If you have a Gaussian prior, it corresponds to just doing L2 regularization over the parameters, right? And we've seen that. But in Bayesian neural networks, what you'd like to do is you'd like to compute this posterior, or be able to compute this posterior, right? And look at the whole ensemble of neural networks. You can't analytically compute it, so you need this posterior in order to make predictions. Given a new point, I'm trying to make a new prediction. I have to figure out what this posterior distribution of the parameters is. And these models are very powerful. Unfortunately, as we will see, computing this term is computationally intractable, so you have to use a lot of computing to figure out what that distribution is. These kinds of methods are now coming back. There are a few workshops at the major machine learning conferences called Bayesian deep learning. So people are trying to figure out how do we, instead of doing point estimate of the parameters, which is what everybody is doing, you have one network, how do you actually compute the whole posterior distribution of all possible networks and then combine the predictions? These models, I think that they work quite well, and depending on what kind of priors you placing over the features, you can do. You can figure out which features are relevant, which features are irrelevant, or which input dimensions are relevant, which input dimensions are not relevant, and so forth. There was actually kind of an interesting story about these models. And I think in 2004, 2005, there was a competition. Back then, people were trying to figure out how do you do feature selection. You have 1,000 features, and you're trying to do feature selection. So you're trying to find a subset of features that are relevant to solving your task. And if you actually use Bayesian neural networks, and it was done by Redford Neal, you don't really need to do feature selection. The model basically figures out on its own what relevant features and what features are irrelevant, or what features are relevant, what features are irrelevant. So it was kind of funny because these methods kind of won the competition. So they had a NIPS workshop, and the aim of the workshop was to do feature selection, and the winning method basically didn't do any feature selection. Basically just by using, to automatically determine what's relevant, what's not relevant, which was kind of funny. In undirected graphical models, right? So this is an example of Ising models. X is a binary random vector. And remember, when we try to compute the probability, Z here is going to be the normalizing constant, also known as the partition function. So you have to sum out over the exponential number of configurations, right? Much like what we've seen in Boltzmann machines. So in this case, if X is 100-dimensional, then we need to sum over 2 to the 100 possible terms, right? So we can't do that. Now, there are some classes of models where the sum might decompose into, or might become tractable if you're looking at the tree-structure graphical models. Otherwise, we need to do some approximation. Right? So anytime we're dealing with posterior inference or anytime we're dealing with graphical models, we always have to resort to some approximations. So for the notation, so most of the situations we're going to be interested in evaluating expectations, right? For example, to make predictions. So we're always going to be trying to figure out what this thing is. What's that, what is that expectation? If we're working with discrete random variables, we're going to be replacing the integral with a sum, right? And then we're going to be also making use of the following notation. We're going to be writing P of Z as a normalized P of Z divided by some normalizing constant. And a normalized P of Z is something that we can, this P tilde is something that we can evaluate. And the normalized is something that we can't evaluate, right? So we can evaluate this quantity, the P tilde, point-wise. So for any Z, we can actually compute what this is, but we cannot evaluate Z. For example, in the case of restricted Boltzmann machines, you could always evaluate P of X, P tilde of X. You could, if this is just would be your free energy. You're summing out the states of the hidden variables, and you can evaluate P tilde of Z. But you can't really evaluate this normalizing constant, right? Because it requires exponential sum. In general, when we're going to be looking at posterior distributions, and that's true for any kind of models, when we look at some posterior distribution, either over latent variables or over parameters, we're always going to be writing it down as a likelihood, the prior, and some normalization. Likelihood we can always evaluate, prior we can always evaluate, but the posterior we can't because we don't know what this quantity is, right? We don't know what the normalizing constant is. For Markov random fields, generally for undirected graphical models, we're going to be writing it as e to the negative of the energy divided by normalizing constant. The energy is something that we can always compute, most of the cases, unless you're getting into more complex models. But we're going to be making assumption that this is something that we can compute, but the partition function normalizing constant we can't compute. Okay? So anytime you're working with for example, things like variational autoencoders and such, essentially we won't be able to compute this quantity. We won't be able to compute the exact posterior over latent variables. When we're looking at RBMs or Boltzmann machines, it's something that we can't really compute these normalizing constants. Okay? So this is the notation. And for example, if you look at deep Boltzmann machine, the problem here becomes even more complicated, is that ultimately we want to be able to estimate both of these expectations. And both of these expectations, to evaluate them, requires basically exponential sum, right? So we can never compute these expectations exactly for models, for expressive models. And that's true for Markov random fields, conditional random fields, and if you've ever encountered these types of models. And both estimations here are intractable, and the reason why is because you can't really compute, these conditionals. Right, so this is something computing this quantity here, which is the posterior over the latent variables, is no longer tractable. So we have to use some approximation to that as well. Okay? So, okay, so how do we deal with these models? Well, the general idea is very simple, actually. If we're trying to estimate this expectation, what we can do is we can draw independent samples from distribution P of Z to basically approximate this expectation, right? So we can say if we actually able to draw IID samples from P of Z, then we can use Monte Carlo estimation to just estimate this quantity. That's the whole idea behind Monte Carlo approximation. You're drawing samples, you're estimating the integrals. One thing to note is that expected value of f equals to the expected value of f bar. Right? The reason why is because if you take an expectation, you can just push the expectation inside, and now you have expectation of f, which is the correct quantity. So that means that Monte Carlo sampling is unbiased, right? Which is a good quantity to have, which basically is telling you that on average, you're going to be getting correct estimates. The variance has this property. You can actually compute this. The variance of your estimator, your Monte Carlo estimator, is going to have this form, right? And there is something nice that's happening to the variance. The variance shrinks as 1 over n, right? So if n is large, you have an estimator that's unbiased, and the variance of this estimate is very small, right? So that's a nice property to have. One interesting thing about Monte Carlo methods is that they don't depend on dimensionality of the problem you're trying to solve. There is no d, the dimensionality that's coming into place. So this variance is not a function of d, right? So it doesn't really depend on dimensionality of z that you're integrating over, which is a very nice property to have, and the variance is decreasing as 1 over n, okay? So why, this seems like a very good estimator. What's wrong with this estimator? Why don't we just use that? It's correct. Its variance is shrinking, significantly. It's unbiased. You get the right answer. Why not just use that one?
It's very hard to draw independent samples.
Yeah, exactly. So one of the things is that you're right. It's very difficult to draw IID samples from distributions. Like drawing an IID sample from Boltzmann machine is very difficult, right? But however, it turns out, based on the result, is that you can actually get very high accuracy with a small number of n independent samples. In fact, there are results that basically show that if you can draw IID samples with like 12 or 20 samples, you can get a reasonable estimate, right? This is heavily used in, in statistics and model design and so forth, or experimental design. So problem one, we may not be able to draw independent samples from the model, right? In many cases, people basically say, if you can draw independent samples from the model, then the problem is, solved halfway through. Like if I could draw exact IID samples from posterior over, some model, you pretty much can compute whatever you need to compute. The second problem to watch out for, if f of z is large in regions where p of z is small, then the expectations may be dominated by regions of small probability, right? So imagine that p of z assigns small value into the region where f is very large, right? Even if you do IID samples, you're unlikely to hit that particular region frequently. But when you hit it, your estimate is going to be very large, right? So that can affect the stability of the estimator, and in fact, the variance of the estimator. Okay? So those are the two things to watch out for. So in general, when we're doing this expectation, for example, if we look at something called predictive distribution, which is heavily used in Bayesian statistics, where you're saying, well, how do I make prediction for X star? And what I want to do is I want to say, what's the prediction of X star given the parameters? And I want to integrate over the space of all possible parameters from, according to the posterior distribution. This is something that, in Bayesian statistics is used a lot, which is, again, comes to the problem, how do I estimate this integral by drawing samples from the posterior? And it might be hard to draw exact samples from the posterior, might be hard to draw exact samples from P of Z. So if you have some complex distributions, P of Z, like this, it's generally very hard to get a really good estimator, right? Because, if you're trying to measure the depth of the ocean, right, and compute some averages, what's the probability you're going to hit this peak? And what's the probability you're going to hit this peak, right? If you don't, your measurement is going to be incorrect. So these are the things to watch out for. Now, let's look at directed graphical models, right? Think of these as sigmoid belief networks and such. So the joint distribution can be specified in terms of the graphical model, right? Remember, we've looked at directed graphical models. We said, well, for directed graphs with no observed variables, sampling from the joint is very simple, right? You sample the states of these latent variables and x4 and x5 and so forth, right? And a pass through the graph, we obtain a sample from the whole joint distribution, right? So for directed models, sampling from the model is very easy, right? Essentially, you instantiate priors, and then you instantiate conditionals all the way down. Now, consider the case that some of the nodes are observed. Suppose that you observe these nodes. That's the observation. Think of it as like an image or a speech signal, or in a language model, these words that you're observing. And then you try to figure out what's the distribution, what's the posterior distribution of other variables in your graph, right? What's the posterior distribution over your latent space? So one thing you can do is you can sample from the model, and if the sample values agree with the observed values, you retain the sample. Okay? So you sample from the model up until you hit the exact values, x6 and x7, and then you retain the sample. Otherwise, you throw the whole sample away. And this algorithm samples correctly from the posterior. This is known as a rejection sampling, the idea of rejection sampling. But the overall probability of accepting a sample from the posterior decreases rapidly, right, with the number of observed variables. So it's very rarely used in practice, right? Imagine if I have my deep belief network, let's say, and I give you the image, and I say, what's the distribution of the latent variables, right? Well, this model would say, keep sampling from your model up until you happen to see this exact image. When you see this exact image, whatever the hidden features gave rise to this image must be the exact sample from the posterior, right? So this is, and again, rejection sampling sometimes is used if you have one dimension or a couple of dimensions. You're kind of just populating the space and trying to figure out exact what the posterior is. So in very small dimensional spaces, you can do that. But in general, you can't. So that idea is to generate samples from non-uniform distributions, but assuming we can generate samples from uniform distribution, right? So one thing we can do is we can define a CDF. We can define cumulative density function. We can sample Z from uniform, and then we can just invert H star to get a sample from P of Y, right? So if I actually compute CDF, then I can sample uniform, do the inverse, and that would be my sample from Y. So effectively, I'm sampling from this axis and then mapping it back to the original space. So here's an idea. So for example, let's say you're sampling from an exponential distribution. I can compute CDF, and then I can sample Z, and then just basically invert it, right? The issue is that computing CDF is just as hard as the original problem, right? So if you actually use a lot of tools, sampling from Gaussian, from exponentials, from Poisson, this is the algorithm that a lot of methods are using. So how do you sample from an exponential? You actually sample from uniform, and then you do the transformation. But in general, for most of the problems, we're going to be considering computing CDF is just going to be just as hard. So we can't really do that. Let's look at rejection sampling and a little bit more elaborate rejection sampling. Suppose we want to be able to sample from some target distribution P of Z, which I'm going to be writing as P tilde divided by Z, right? And Z is some normalizing constant. So we have this red curve is specifying some multimodal complex distribution, right? Now, suppose that we have an easy to sample from proposal distribution. Think of the proposal distribution maybe being a Gaussian, or something that we can draw samples from, such that, this is going to be Q distribution, such that there is some constant K, such that K times Q of Z is always bigger than P tilde of Z. Okay? In other words, I'm defining some constant K such that it covers overall my P tilde distribution, right? In some cases, you can do that. There is also a more elaborate class of models called adaptive rejection sampling, which essentially tries to construct a piecewise approximation to the red distribution. So there are elaborate techniques for doing that. But let's say you can do that. Now, here's the algorithm. You want to sample Z from Q, right? Which is something you can sample from. Then you're going to be sampling U from uniform from 0 up to K times Z, right? So let's say you've sampled Z sub 0 over here, right? So you're sampling Z sub 0 from your Q distribution. And then you're sampling U sub naught from uniform between 0 and K times Q of Z0, right? So you're sampling along this line uniformly, right? So what that means is that the sample Z and U has uniform distribution under the curve, under the blue curve. That's exactly, that's exactly the meaning of, uniform sampling under the distribution K times Q of Z. So it's uniform sampling under the blue curve. So if U sub naught is bigger than P tilde, right? So it's bigger than this thing, your sample is rejected. Otherwise, the sample is accepted. Okay? Does that make sense? So this is called rejection sampling, right? Because effectively, if you have a sample, uniform sample under the blue curve, then you're just measuring, did you hit uniformly below the red curve or above the red curve? If it's below the red curve, you retain the sample. If it's above the red curve, you throw it away. And this will give you IID samples from the red distribution, right? Now, let's look at the probability of the sample being accepted. The probability of accept, what is the probability of being accepted? Well, remember, you're sampling from Q, right? And the probability of retaining a sample is P tilde divided by K times Q of Z, right? It's the ratio between, it's the ratio between how big this thing versus how big the line is to the blue curve, right? That's the probability of accepting. And you're taking an average over the entire, taking expectation over the entire curve Q of Z, right? So essentially, it comes down to just looking at this quantity here. And the fraction of accepted sample really depends on the ratio of the area under the P tilde versus the area under K times Q of Z, right? It really depends on the ratio of this area and the area under the red curve. So if you're able to approximate the red curve fairly precisely, then your acceptance is going to be pretty high. Otherwise, your acceptance rate is going to be pretty low, right? It's also very difficult to find Q of Z with optimal K, right? So rejection sampling, again, in this case, you can use it in few dimensions. Sometimes rejection sampling is also used as sort of an algorithm that sits inside a bigger sampling algorithm. We'll see some examples of that. Here's an example of rejection sampling. Let's say your target distribution is a Gaussian distribution with some variance. But let's say, you can't really sample from this distribution. And now you have some proposal distribution, again, with some different variance, sigma sub q. We must have sigma sub q has to be bigger than sigma sub p, right? Because it has to cover the overall distribution. And then the optimal k you can compute, but the optimal k is going to be given by the ratio of the standard deviations, raised to the power of d. So whatever the dimensionality of the problem you're trying to solve. So that means that the acceptance rate will diminish exponentially for this very simple example, right? And this is in order to be able to ensure that your Gaussian, your red Gaussian covers the green Gaussian, right? So even if you could come up with an optimal distribution, again, the acceptance rate will diminish exponentially depending on dimensionality of your problem. So it's a useful technique in 1 or 2 dimensions. People typically use that. And it typically applies as a subroutine for more advanced techniques. Okay? It's a very useful technique if you can find the right proposal distribution to sample from. Importance sampling is another technique which is heavily used also in practice. It has, it's sort of the idea of it is, I think, to some extent it's comparable to rejection sampling, so there's no magic here, but it's a little bit different. So suppose we have an easy to sample proposed distribution Q such that the only requirement is that Q has to be non-zero wherever P is non-zero. Okay? So let's look at computing this expectation. Again, I can multiply and divide by Q, right? This is something similar to what we've seen in variational inference, right? Where Q is some easy to sample from distribution, some easy distribution we can optimize over. We can multiply and divide by Q, and then we can form this estimator. We can sample from Q, right? And then just compute this quantity here. Okay. Now, the quantities P over Q are sometimes known as importance weights, right? It's telling us how important a particular sample is, right? If Q of Z is smaller than P of Z, that basically means that the sample is very important. Otherwise, it's not as important. Unlike rejection sampling, in this case, all samples are retained. You never throw any samples away, right? So that's generally is the case. But one of the things you might want to look at this is to say, well, what if I'm actually facing this problem? Let's say it's my Boltzmann machine, a graphical model. So I don't have a partition function, right? So how do I actually compute? Let's say Q is my Gaussian distribution, or some simple distribution. I look P over Q, but I'm making an assumption that P is actually normalized, because I'm looking at the normalized ratio of the two in order to compute these expectations. So what can I do? It turns out that you can actually solve this problem using importance sampling as well. So let our proposal distribution be of this form, right? Q is going to be Q tilde be divided by some normalizing constant. In the case where Q, and again, our assumption is Q is something simple. So think of a Gaussian distribution. The Gaussian distribution Q tilde could be the exponential, like e to the negative squares. And your normalizing constant could be, 2 pi square root of sigma squared, right? So that's your normalizing constant. Now, what I can do is I can do the following. The expectation with respect to P, some complicated distribution of my function f, whatever that f is, I can write this down. I can multiply and divide by q. And now what I'm going to do is I'm going to write it down this way. Right? I'm basically going to say, instead of p, I'm going to represent p as p tilde divided by the normalizing constant of p. Q, I'm going to represent as q tilde divided by normalizing constant of q. And so now I have this ratio of partition functions. I can compute z sub q, but I can't really compute z sub p, right? But look, this thing I can compute, right? Because these are just unnormalized quantities. So this is something I can compute. So using importance sampling, I can come up with this expression. So z sub q divided by z sub p is, again, something that I can't compute. So what do I do here? It turns out that we can use the exact same weights to actually compute this ratio. Right? So let's look at what this ratio is. It's 1 over z sub p, or 1 over z sub q. What's the definition of z sub p? Well, the definition of the normalizing constant is just this integral. Right? That's the definition. That's a normalizing constant. And so now what can I do? Well, I can write this thing as p tilde over q tilde times q. Right? The reason why I can write it this way is, remember, what is q tilde? Or what is q? Q is q tilde divided by z sub q, right? So these things would cancel, and then you have this partition function here. And so now all of a sudden I have exact same form as I have over there. So what is this thing here? It's just the average of the importance weights. So if actually I want to compute and the expectation, I'm going to be drawing samples from Q, right? Computing these weights, which is the ratio of unnormalized ratio of P over Q, and then I'm just going to normalize the weights. So that's nice. So it's sort of, you compute these weights, they're always positive. You divide it by sum of the weights, and then you take the average, right? So these weights, it's almost like they'll sum to 1. And this is a very commonly used practice for example, there are extensions of something that's called wake-sleep algorithm or reweighted wake-sleep algorithm. There is some extensions of autoencoders, variational autoencoders. So a lot of different techniques are relying on this expression. Very simple expression, but when you apply it to sampling from more complex models, it's actually working pretty well. Okay? Now, this estimator is consistent, which basically means that as you keep drawing more and more samples, it will converge to the right value. But unfortunately, it's biased. It means that this expectation, this estimator, if I take the expectation of this estimator, it will not necessarily be equal to the true expectation. Right? So asymptotically, you will converge to the right value, but it's a biased estimator. Any guesses why it's a biased estimator? We've just seen that, Monte Carlo, if you kind of like draw samples, take expectations, it's going to be unbiased. On average, it's going to have the right value. Any guesses why this is biased?
It's finite sum.
No. The reason why it's biased is because if you look at the expectation of these importance weights, right, of the ratio, this quantity is unbiased, right? The issue is that when you have an unbiased quantity and you divide it by another unbiased quantity, the ratio of unbiased quantities doesn't mean that it's going to be unbiased. It might actually be biased, right? So if the expectation on the top is correct, expectation on the bottom is correct, the expectation of the ratio might not be correct expectation, right? So that's why. Whenever you have two quantities and you divide them or you multiply them by, it doesn't really mean that the end product is going to be unbiased. So that's generally is the case. Now, with importance sampling, unfortunately, it's very hard to estimate how reliable the estimate is, right? You can have very high variance If the proposal density is small in regions where FZ, P of Z is large, right? Generally, it comes down to the same problem that if Q of Z has some small probability where this quantity, Fz, P of Z, is very large, then your estimate is going to be very unreliable. It's going to have huge variance, right? Here's an example of using Gaussian distribution as a proposal in one-dimensional case, okay? So you try to estimate the value of some expectation, the sum distribution P in one-dimensional case, and your proposal is Gaussian. After basically, in this case, 1 million samples, like you look at this thing, you say, okay, it's converged. But it's actually far from the ground truth, from the true expectation. And you can see it can even after 1,000 samples, it can isolate. And in after 100,000 samples, it can oscillate as well, right? And this is in one dimension, so it can have huge variance. So here is another example. Here's another example of using Cauchy distribution as a proposal in one-dimensional case. In this case, after 500 samples, the estimator appears to converge. One of the things you need to ensure when you're using sampling-based methods is that your proposal distribution should have heavy tails, right? Because in the Gaussian distribution, the tails fall off exponentially, right? So the probability of sampling in the tails is exponentially small. But if the value of your, of the target distribution is high, your estimate is going to be very wrong. Is always going to be wrong. So here's the idea: is that your proposal distribution should, you should have heavy tails so that you, try to cover as much space as possible for sampling-based method. This is just one example of that. You can look at the book with a whole lot more examples that kind of look at this problem. Generally, just like rejection sampling, simple important sampling techniques are used mostly in 1 or 2 dimensions, or in simple cases. We have to do something more advanced in order to be able to solve this. And there's a whole spectrum of different techniques that take this idea, important sampling idea, and kind of extend it to working in high-dimensional spaces. Okay, summary so far. If our distribution Q of Z poorly matches the target distribution, then rejection sampling almost always rejects. You throw things away, wasting your computation. Important sampling will have large, maybe possibly infinite variance. So your estimate is going to be very unreliable, right? So these are very simple techniques. Generally, for high-dimensional problems, they will not work well. So for high-dimensional problems, finding a good proposal distribution is very hard, right? Unless you know what the shape of it. Remember what happened in the variational learning. In the variational learning, we say, well, here's our proposal distribution Q, and now we're actually going to be optimizing for the parameters of this proposal distribution to match the variational bound, to try to make our variational bound be as tight as possible, right? So we're effectively almost like learning what the parameters of the Q distribution should be. And there are ways of extending these ideas to being more adaptive. And as I mentioned before, there's something called adaptive rejection sampling and so forth. But generally, it's fairly difficult to do, right? So what can we do? Well, there's another class of algorithms called Markov chain Monte Carlo based methods that basically allow you to solve these problems. So let's look at the Markov chains. At least let's start looking at the Markov chains, because that's a topic that you can take a course on CMC. How many of you have ever seen Markov chain Monte Carlo based methods? A few. You can probably take a whole course in statistics on these methods and study the property of these algorithms. These algorithms, again, are heavily used in statistics. And the reason for that, as I mentioned in the last class, is that they have properties of the form that asymptotically, you will get the right answer. As your Markov chain will converge, you will get the right answer, right? Variational inference methods, on the other hand, your approximation is always going to be an approximation. You will never get the right answer unless, the family of approximating distributions actually includes the correct distribution or the true distribution, which is never is the case. So depending on your philosophical views, you can stick to one versus another. But let's look at Markov chain methods. You have a series of random variables, right, such that the following conditional independence property holds. So we're going to be saying the conditional probability of Zn plus 1, conditioned on the entire past history, is just going to depend on the previous time step, right? It's just going to be given by conditional probability of P of Zn plus 1 given Zn, given a sequence of samples, right? So we can specify the Markov chain by the probability distribution of the initial state, okay, P of Z1, by the conditional probability for subsequent states in the form of transition probabilities. So we're going to be using this notation, which is heavily used in statistics, which is this transition operator. The transition operator is basically saying, how do I move from state Zn to state Zn plus 1 to the next state? And this transition operator is just going to be given by the conditional probability, right? It's the probability of Zn plus 1 given Zn. Now, this transition operator, we'll have to specify what that is, right? Or, in many cases, we're going to be setting this transition operator to have a specific form, okay? But think of it as defining this transition operator, really defining the conditional probability of moving from one state to the next state, okay? Think of discrete random variables. So this conditional probability is just going to be a table, right? In the continuous case, these transition probabilities are going to be densities, right? Specifying a probability density function of moving to the next state given the previous state. And sometimes these transition operators are often called transition kernels. So a marginal probability of a particular state can be computed as such, right? So the probability of Zn plus 1 is going to be equal to sum over all states Z sub n. You have a transition probability of moving from Zn to Zn plus 1 times the probability of Zn, right? That should be very clear, because what is this saying? Again, this transition kernel is just the probability of Zn plus 1 given Zn times probability of Zn summing out over Zn. This is just a simple rule of probabilities, right? So you can always compute the marginal. Now, a distribution pi of Z is going to be called invariant or stationary with respect to the Markov chain if each step in the chain leaves pz invariant. If this holds. So P of Z, think of it as a marginal distribution. It's called stationary distribution if this equality holds, right? I take the marginal distribution of under my stationary distribution of Z prime. I look at the transition, the conditional probability of moving from Z prime to Z. I sum over all possible configurations of Z prime, and I get my marginal distribution, which matches P of Z, right? So think of it intuitively as that if I get a sample from P of Z, and I start applying these kernels, these transition kernels, my marginal distribution will not change, right? Now, a Markov chain, right, which specifies these conditionals, can have many stationary distributions. For example, the identity transformation, right? The identity transformation can be if I'm in state Z prime, stay in the same state, right? This basically is the identity transformation, so any distribution is invariant, right? So if my pi of Z is some Gaussian, and I say my transition kernels just don't do anything, then it's a stationary distribution, right? According to this transition kernel, any distribution is invariant, right? Does that make sense? These are just some definitions, and we'll see some examples of why we need these properties. Now, sufficient but not necessary condition ensuring that P of Z is invariant is to choose a transition kernel. So you specify what this conditional probability is that satisfies so-called detailed balance property, right? And again, this is just a reminder, the transition kernel of going from Z to Z prime is just a conditional probability that we have to specify. And the detailed balance property basically says, well, pi of Z prime, it's my marginal distribution of Z prime, and then transitioning from Z prime to Z is the same as pi of Z and then transitioning to Z prime given Z. Okay? If this property holds, then it's a sufficient condition for pi of Z to be invariant. So a transition kernel, T, that satisfies this detailed balance equality, this condition, will leave that distribution invariant. Right? And the way to think about this is very simple. If I sum over Z prime in both cases, what is this going to be? So what is this? By definition, if I sum over Z prime, this is just going to be P of Z. I can pull it out of the sum because it doesn't depend on Z prime. And by definition of the transition kernel, this has to be 1 because it's just a conditional probability. So if I sum over all possible states, it's going to give me P of Z, right? So if I can construct a transition kernel that satisfies this property, I can guarantee that it will leave that distribution invariant. Okay? Now, sometimes a Markov chain that satisfies this detailed balance is said to be reversible. And there's a whole lot of work on something that's called non-reversible Markov chains. But generally, we're only going to be looking at kind of simpler ones, is reversible. Okay? Any questions here? Let's look at the example. Let's look at a very specific discrete example. Suppose that I have some distribution, P star, over the 3 random variables. Probability of being in the first state is 3 over 5, second state 1 over 5, third state is 1 over 5. And then I have my transition kernel. And the transition kernel is the probability of moving from state 1 to state 1 is 2 over the third. The probability of moving from state 1 to state 2 is 1 over 6. Probability of moving from state 1 to state 3 is 1 over 6. Right? And then probability of moving from state 2 to state 1 is 1/2 and so forth. Right? So you're seeing that these numbers sum to 1. 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 Right? This is my transition kernel. Okay? Because these just specifies the conditional probabilities. In this case, P star is invariant. Is invariant distribution of T because if I take this distribution P star, multiply it by T, I'll get back P star. Right? Or this property holds. If I take P star and I sum over all possible transitions out of P star to Z, I'll get P star of Z. I'll get the marginal distribution. Right? And P star is also called equilibrium distribution because if I start at any other distribution and I follow up using the transition kernel T, eventually I will converge to P star. Right? In practice, what does that mean? In practice, that basically means that if I get samples, this is my initial distribution, let's say. I start from state 1 all the time, or some other distribution. And I evolve my sample according to these transitions. Eventually, my marginal distribution will be P star. Right? So if I actually plug in any distribution here, I raise this matrix to the power of 100, and basically means I apply this transition operator. In all of the cases, you will get to P star. Does that make sense? So that's what it means for T, or for P in this case, to be invariant with respect to T, or to reach equilibrium distribution of T. Right? Now, why are we sort of doing it that way? The idea behind MCMC methods is actually pretty smart. What we're going to be trying to do is we're going to be trying to say, okay, P star is our true distribution, true posterior distribution of interest, posterior distribution over the latent variables, or true distribution from a Boltzmann machine, right? So P star is something that it's very hard for us to sample from. We don't know how to sample from. What our goal is going to be is to come up with transition kernel T in such a way that if I apply this transition kernel, eventually I will reach my true distribution of interest. I will reach my true posterior distribution or distribution of Boltzmann machine or whatever that distribution is, right? So I'm going to design a sampling algorithm. I'm going to design what my T should be, what my transition operator should be in such a way that if I sample according to this transition operator, eventually I'm going to be sampling from P star, right? Or if I average over my samples, my marginal distribution is going to be P star. Does that make sense? So here it's the other way around. It's like here is the kernel, and P star is my target distribution. We're going to do it the other way around. We're going to say P star is going to be distribution of interest, some complex distribution, and we're going to learn how to construct transition operators so that we eventually hit the distribution of interest. Okay, so we want to sample from the target distribution, for example, posterior distribution or some more like a Markov random field model, whatever that distribution is, right? And we're going to set it up by setting P to be P tilde divided by Z. That's what we want to be able to sample from. And as we know, getting IID samples is difficult. And what we're going to do is we're going to set up a Markov chain with specific transition kernel T. So we're going to define what that kernel T is that leaves our target distribution P of Z invariant, right? That means that if we have a sample which we will evolve according to this transition kernel T, eventually this sample will be a sample from the target distribution. If the chain is ergodic, then the chain will converge to unique equilibrium distribution. And ergodicity is sort of, state I is said to be ergodic, and it's a periodic positive recurrence. Essentially what that means, you can look at more technical terms, but essentially what that means is that there should be some probability of going from any state to any other state. Okay? Obviously, if the probability of going from some state through a bunch of these transition kernels to any other state or to some other state is 0, then you cannot hope to reach correct answer because there's no way for you to jump from this state to this other state. In generally, the way that we're going to be defining these transition kernels they're going to be ergodic. And again, there's more technical conditions if you're interested in looking at what that means. But essentially for us, it would basically mean that there's always some probability of going from one state to any other state. Then, once we set up this Markov chain and we evolve our samples according to the Markov chain, we obtain dependent samples drawn approximately from P of Z by simulating a Markov chain for some time. If you remember your second homework, in your second homework, you were sampling using Gibbs sampling from your model, right? You were sampling states of the hidden variables and visible variables, hidden variables and visible variables, and so forth, and you did it for 1,000 time steps. What you were doing is exactly setting up a Markov chain. It's called a Gibbs sampling, but you were setting up a Markov chain such that as you evolve your samples according to this Markov chain, after some time in the future, these samples would approximately be samples from the model, right? And that's exactly, if you set it up this way, then you can show that eventually you will reach the target distribution and the sampler will converge or the chain will converge to the unique equilibrium distribution. It's not like you start with one point, you reach some distribution. Start at another point, you reach some other distribution. No. You will reach the correct distribution. And again, ergodicity here basically says that there exists some K such that for any Z, for any state, there is a probability of transitioning to any other state under which your target distribution has non-zero probability mass, right? Does that make sense? Okay. In practice, we're going to look at construction of these transition operators, but in practice, we often construct the transition probabilities from a set of base transition probabilities, B1 up to Bk. So you might have, a whole bunch of these transition probabilities, and you can also look at a mixture distribution, commonly used. So your transition operator could be some weighted average of base transitions. These mixing coefficients have to sum up to 1. We'll see some examples of that perhaps later in the class. Another option is to combine these transition operators through a successive application of these transition operators. So in many cases, these kinds of operations are used when you update one dimension at a time. So you update one dimension of your latent space, you update another dimension of your latent space, another dimension of latent space, and so forth. And you chain all of these things up, and then the sample that you get is this, is a transition from one state to the next state. And if the distribution is invariant with respect to each of these base transitions, then it's also invariant with respect to, the overall transition operator. So these are just different ways that people come up with different transition kernels, and how you can combine them. Couple of technical things I want to point out is that in the case of the mixture, if each of the base distributions satisfies detailed balance, then the mixture transition will also satisfy detailed balance. Okay, so that's good. Basically, that means that your transition kernel will satisfy detailed balance, which basically means the correct transition operator to use. For the case of using composite transitions, this might not hold. And typically what people do is people sometimes symmetrize the order of application of the base distributions. This is some... Whoa. Hold on a second. This is something that's... sometimes when you look at the papers, you apply dimension 1, dimension 2 up to dimension k, and then in reverse. Again, this is just to point out, this is a little bit more elaborate. We're not going to be using this, but sometimes people do combine multiple transition kernels. So in this case, a common example is using these composite transition probability where each base transition changes only a subset of variables. So if you're updating one dimension at a time. We have about 5 minutes, so let me give you the definition of Metropolis-Hastings algorithm, and the next class will come back to this particular algorithm. It's a very famous algorithm. It was developed back in the early 50s by, there's a team, I guess it's called Manhattan Project. They were basically developing a nuclear bomb. And they needed to compute expectations of a high-dimensional, high-dimensional problems. And so Metropolis and his team basically developed this algorithm to be able to compute expectations properly, to, I guess, calibrate certain things. It's kind of funny. But it was kind of, the algorithm was really developed as part of Manhattan Project, right? You know what Manhattan Project is. This is basically where he developed a nuclear weapon in the 50s. And it's kind of an interesting story because they had to compute these high-dimensional expectations. They didn't know how to do that, so they came up with an algorithm. The algorithm actually requires sampling from some proposal distribution. So let's look at the algorithm. The algorithm basically says the following. So the Markov chain transition operator from current state z to state z prime is defined as follows. So we're going to be sampling a new candidate state z prime according to some proposal distribution q z star given z. Okay? So proposal distribution could be simple distribution. Again, think of it as a Gaussian distribution or Bernoulli distribution if you're working with discrete random variables, something simple. Okay? Now, a candidate z is accepted, so you're retaining the sample with this probability. And this probability is the minimum between 1 and the ratio of unnormalized probabilities of p tilde of z divided by p tilde of z, or p tilde of z star divided by p tilde of z, times the ratio of this kind of adjustment probability. What's the probability according to Q distribution of moving to z given z prime, or from a Q distribution of moving from z prime to z, or z star to z, right? For now, if you're using Q distribution which is symmetric, think of it as a Gaussian distribution. Gaussian distribution is symmetric. If I have, if I'm a particular state, I put a Gaussian around me and say, what's the probability of moving to some other state? And then I say, well, if I'm in this state, under the same Gaussian, what's the probability of moving back to this state? These probabilities are the same, right? Because they have the same variance, same thing. In which case, this ratio will be 1. This ratio is essentially saying, if I propose z star, would my normalized probability be higher compared to my original z? And if it's higher, I'm going to accept it. If it's low, I'm going to only accept it with some probability, right? If it's low by half, I'm going to accept it with probability half. So intuitively, what this algorithm is doing, this algorithm is kind of defining a Markov chain as it tries to move into regions where P has high probability mass, right? So eventually, we'll be moving in the spaces where this pi will have higher probability. If accepted, you're basically setting up the new state to whatever you sample from. Otherwise, your new state becomes the old state. And the next state is just a copy of the current state. Okay? It's a very simple algorithm. Notice that you don't need to know anything about normalizing constants for your distribution pi, right? So if you want to sample from the posterior, if you want to sample a space of latent variables, pi tilde is just likelihood times the prior, which is something that you can compute. Or it could be the energy function, exp of the energy function, negative of the energy function. Again, it's something you can compute. And this algorithm will guarantee that as you sample according to this algorithm, you will eventually be sampling from distribution pi, right? So if pi is my posterior, then as I run this algorithm, eventually you'll get samples from your target distribution. There are no approximations here. You will be sampling from the correct distribution. Now, if you ask the question, how long, are there specific bounds you can define? Generally, the answer is that unless it's a very specific cases, you can define how long it will take. For most general problems, you can't. It's very difficult to say, this is my problem, I run it for 1,000 steps, and I can guarantee that my sample is going to be a true sample from the posterior. But the interesting thing is that Metropolis defined this algorithm. Hastings in the 60s came up with this adjustment. So your Q distribution doesn't have to be symmetric. Your Q distribution could be, skewed, right? And that's the adjustment that you take into account. It's also interesting that when we're computing expectations, because once you get samples from pi, which is your complex distribution, once you get samples from pi, you can then compute expectations, you can compute whatever you need to compute. Once you have samples from distributions, you can do a lot of things, right? And it's interesting, I think the story goes that at that time, they really didn't have a good random number generator. So how? Because this algorithm requires you to draw IID samples from Q, right? So they had a bunch of people flipping coins to figure out how do you actually draw ID. You couldn't, because otherwise the algorithm doesn't work if these are not ID samples. So if you flip coins, then you can take this randomness and construct the distribution samples from distribution Q, which is kind of interesting. They literally, my understanding is that they literally had a bunch of people flipping coins to get IID samples, and they were able to compute quantities that they needed to compute fairly precisely, which is something that you couldn't do before. And notice that this algorithm also doesn't depend on dimensionality of the problem, which is another nice property of this algorithm. It doesn't really tell you anything about, the only thing you need to do is you need to compute unnormalized probabilities. So for example, with RBMs, right, and there are some important sampling techniques where you choose some simple distribution, Pi tilde would be just the energy function, the free energy function. Right? You're integrating over the states of the hidden variables. You have a normalized probability. You can compute exactly. So there is no need to compute normalizing constants or partition functions of any kind. And as I mentioned, for symmetric proposals, for example, a Gaussian distribution centered around your current state with some variance sigma, the acceptance probability basically reduces to this quantity. And then there is a whole bunch of algorithms. It's called adaptive MCMC algorithms. They essentially try to figure out how do you adapt your Q distribution. And how do you adapt your Q distribution in such a way that you're able to explore the space more efficiently while at the same time not violate, the convergence properties of the algorithm. So there's a lot of work, people trying to figure out what's the optimal distribution Q. The other thing you have to figure out is what's the optimal acceptance rate. Acceptance rate of 1 is not very good because that means that you're making very, very small steps because you're always accepting. It's like myopic. If you're making large steps, you're kind of looking around, your acceptance rate is going to be very high because you might not hit the right parts of the distribution. And then there are some papers showing that the optimal acceptance rate is 0.277, according to some metrics. You know what? Let me just show you the proof, and then we'll come back to the proof in the next class very quickly, just to give you the idea of how do you set it. But again, if we come back to this algorithm, exactly what we were doing is we're constructing this transition kernel, right? We're constructing these conditional probabilities in such a way that as I sample according to these conditional probabilities, I can reach my target distribution, right? Does that make sense? So let's look at the Metropolis-Hastings transition kernel that leaves PZ invariant, showing that it actually satisfies detailed balance. Because if it satisfies detailed balance, it means that it leaves pi distribution invariant. So let's look at what this quantity is. Pi z times transition of z prime given z, right? So what is z prime given z? Well, z prime given z is given by q of z prime given z, because that's you sample from q, that's your proposal, times the probability of accepting it, right? Times this minimum of 1 pi divided by pi and so forth, right? I can always rewrite, I can always pull pi of z, q z prime given z, I can pull it inside, right? So I can write it as a minimum of 2 terms. I can pull the other term back, this quantity, and then I can write it this way. Okay? If you actually stare at the equations, you will realize that it's pretty trivial. You're essentially just rearranging the terms. And then you have to kind of ensure that whether the chain is ergodic will depend on particulars of the station distribution pi, and more importantly, proposal distribution q. Right? So typically q, if q is a Gaussian, or if q is some independent Bernoulli variables covering the whole space, if you're working in the discrete set of distributions, then you're okay. Right? So that's a very simple proof. So let's stop here, and then we'll come back to Metropolis-Hastings algorithm next time. And we're going to look at Gibbs sampling algorithm and a few other extension of these algorithms. And that will give us a good way into looking at the space of variational autoencoders, where we're going to be using both variational inference and extensions of it by using sampling-based algorithms. Okay? So I would advise, this week you have project proposals, you have assignment. We will not have a class this Wednesday. So take time, finish your assignment. But at the same time, please look at the reading material for variational inference for MCMC. Because if you don't, then you will probably not follow the lectures on variational autoencoders as well as other kinds of models, including generative adversarial networks. Okay? Okay.